In this video, I'm going to be going through an example of titrating a strong acid with a strong base. So the question says a 20 milliliter sample of 0.125 molar nitric acid is titrated with 0.15 molar NaOH. Calculate the pH for at least 5 different points throughout the titration curve and sketch the curve. Indicate the volume at the equivalence point on your graph. Here's the important information. The important information I've highlighted. And the key is that we need to calculate the pH for 5 different points. So I've chosen 4 random points, and you have done 5 points. In this video, I'm only going to do 4. So a good point to always have is the initial amount before we add any base, just with our acid. You could have picked 5 milliliters, 15 milliliters. I just picked 10 milliliters, 30 milliliters. And then another good point to have is the equivalence point. The initial point and the equivalence point are really key for drawing a good titration curve. The other points, you could have picked different volumes of NaOH. So we're going to start by calculating the initial pH. So this is when we have 0 milliliters of NaOH. So in our beaker, all we have is HNO3. That's all that's in that beaker. And nitric acid is a strong acid, so therefore the pH, as we know, is equal to the negative log of our H3O plus. And in this case, if we have 0.125 molar HNO3, that means we have 0.125 molar H3O plus, because our HNO3 is in water. It's a solution, so it's mixed with water, and it fully disassociates. So all of it becomes H3O plus plus NO3 minus. So all of our HNO3 becomes our H3O plus. So let's calculate our pH. So that's just the negative log of our concentration, so 0.125. You get a pH of 0.903, which is what we'd expect because all we have is a strong acid, so our pH should be very acidic. So let's go to our next point. Now we have 10 milliliters of sodium hydroxide. So what's happened is that we have added sodium hydroxide to our nitric acid solution. And this is going to produce water and sodium nitrate. So if we've added 10 milliliters of NaOH, we need to figure out how many moles of NaOH we have, so that way we can figure out how many moles of nitric acid have actually reacted. So we're going to convert this into liters and then into moles. And this 0.15 moles of NaOH per 1 liter is the molarity of our NaOH. Remember, moles over liter is the same thing as big M, as molarity. So now my milliliters cancel out, my liters cancel out, and I'll be left with moles. So I'm left with 0.0015 moles of NaOH. I see that I have a 1-to-1 ratio between my base and acid, so I'm going to convert this into my nitric acid. So for every 1 mole of sodium hydroxide, there is 1 mole of nitric acid, which means that 0.0015 moles of sodium hydroxide will react with 0.0015 moles of the nitric acid, HNO3. Okay? So, this is how much base I have. How much acid do I have? So I need to do the same thing with my acid. And notice with my acid, I'm given 20 milliliters and 0.125 molar. So I'm doing exactly the same thing. So 20 milliliters of nitric acid, that is 0.125 molar nitric acid, is really 0.0025 moles of nitric acid. So if I start with 0.00 0.0025 moles of nitric acid and 0.0015 moles of sodium hydroxide, I need to figure out what's going to run out first. Well, down here, I have already calculated that with 0.0015 moles of sodium hydroxide, 0.0015 moles of nitric acid will react. So if I have 0.0015 moles of sodium hydroxide, that means 0.0015 moles of my nitric acid will react. So this reacts totally with the sodium hydroxide, so I'm left with 0 moles of sodium hydroxide, and I'm left with 0.001 moles of nitric acid. I'm just going to clear this. So this is how much nitric acid I now have, and now I need to calculate my pH. Well, pH is equal to the negative log of the concentration of H3O+, which means I need to calculate the concentration, not just the moles. I need the molarity. So I know that my total volume is equal to the 20 milliliters of acid I have plus the 10 milliliters of base, so it's 30 milliliters. So my molarity, or moles over liters, is 0.0010 moles all over. So I'm going to be taking the negative log of 0.0010 moles all over 0.030 liters. And again, that's my total volume and my moles of nitric acid. So therefore, my pH is 1.477. And that's at 10 milliliters when I add 10 milliliters of base to this solution. So now I've added 30 milliliters of base. So again, we're going to do the exact same thing. I need to calculate my moles of base present in my solution, my moles of acid present in my solution, and then figure out which one is left over after they react with each other. So here I've calculated my moles of sodium hydroxide and my moles of nitric acid. Notice I have more moles of sodium hydroxide than I do of nitric acid. So that indicates to me that the nitric acid is going to totally react, and I'm going to be left over with sodium hydroxide. In this case, the nitric acid is my limiting reactant. So I'm going to have sodium hydroxide and nitric acid. And I have 0.0025 and 0.0045, and this is in moles, and 0.0025 is going to react. Okay, so now I'm left with 0 moles of HNO3, and I'm left with 0.002 moles of NaOH. So again, this is my moles of NaOH. So I know that POH is equal to the negative log of my OH minus. And I'm doing that because I have my base left over, my OH left over. So I can easily calculate my molarity of the OH. Now remember, this is moles. Here's my total volume. So my molarity should be 0.002 divided by 0.05, which is 0.04. So my POH is equal to the negative log of 0.04, which is equal to 1.398. So therefore, my pH is equal to 14 minus that number, which is 12.602. So when I have 30 milliliters of NaOH, my pH is 12.602. The last thing we're going to calculate is the equivalence point. Now, the equivalence point tells us that the moles of HNO3 is equal to the moles of NaOH. We've already calculated our moles of HNO3. It doesn't change because we're not changing the amount. So we have 0.0025 moles of HNO3. Okay, we're trying to get the same number of moles of NaOH because it is a 1-to-1 ratio, as we have already established. So I know that due to the concentration of NaOH, I know that in 1 liter of NaOH, I have 0.150 moles. Therefore, my volume at the equivalence point of my sodium hydroxide will be 0.0167 liters, which is equal to 16.7 milliliters. So this is at the equivalence point. I also know that I'm titrating a strong acid with a strong base, and whenever you titrate a strong acid with a strong base, the pH is equal to 7. Because, remember, in our equation, we're forming water and a neutral salt. So if all of my sodium hydroxide and all of my nitric acid react, the resulting solution is totally neutral, which has a pH of 7. So now we have 4 different points. We have our first point is at 16.7 milliliters, there's a pH of 7. Our second point is at 30 milliliters, there's a pH of 12.602. Our third point is at 10 milliliters, there's a pH of 1.477. And the last point is at 0 milliliters of NaOH, there's a pH of 0.903. So now we plot these on a graph with the x-axis being the volume of NaOH and the y-axis being the pH. So here I've plotted all 4 of the points that we calculated, and I know that near the equivalence point, it's pretty much a vertical line. So my titration curve is going to look something like this. And that's it.